The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
First of all, welcome to the families. It's family weekend, so welcome to the parents, SIBs, and other members of extended family. I hope you have a lovely weekend on campus, and especially welcome to 3091. I have nothing special planned today, just a run-of-the-mill lecture so you get a sense of what it's like to be sitting in one of these seats that you've paid so dearly for. I hope we can convince you that you've made a smart decision in putting your son or daughter on this campus. You'll come to the quick conclusion it's not because of the facilities. Facilities here are nothing special. The classrooms, the labs, and so on. It's the peer group. It's not the faculty. Faculty are okay, but I think it's the peer group. I think it's the students that are going to be the friends and colleagues that makes it a special experience here. I'm teaching freshman chemistry, but it's taught from the Department of Material Science and Engineering. And I just want to make one little plug. If you walk up and down the Infinite Corridor, by and large it's ugly because it's decorated with administrative offices, with one exception. As you get to the east end, it looks like an engineering school because there are labs associated with the Department of Material Science and Engineering. And if you ever wonder what's going on in those labs, it's your chance to find out. So this afternoon from 3:30 to 5, it will be possible to tour the undergraduate laboratory, which is on the south side, and the nanomechanics lab on the north side. So if you're finding uncomfortable silence with your son or daughter and things are kind of dragging on, walk down to the east end of the Infinite Corridor and you can see some interesting things. They're going to have some demos and whatnot. And for the other announcement is that on Tuesday we will have Quiz 6 based on Homework 6, but there's a few questions on Homework 6 touching upon X-rays, and at the rate we're going, we will not have covered that material. So ignore the questions on X-rays, but the rest I think you should be familiar with. And we'll test at the end of the period instead of the beginning. That way you'll have some time to interact with the recitation instructor. So what I want to do today is something really important, and it's fitting that the parents are here. Up until now, by and large, perhaps with the exception of some of the band gap material, what we've been covering, you could have seen bits and pieces of that in high school. And if you've taken a lot of high school chemistry, you might be familiar with it. Well, starting today, say goodbye to high school. This is solid-state chemistry now. That's why we have the crystal models up here. And what we're going to do is we're going to begin with a little bit of a review. And so if you'll take a look at the handout that's going around, this will, of course, be posted on the web afterwards. But just to follow along, I know the parents are here. It gives them some comfort factor to hold a piece of paper in their hand. So that's your Linus blanket for this morning. So I want to give the big picture. And the big picture is that the thesis of 3091 is that electronic structure informs bonding, which then informs state of aggregation. And just to remind you, we started back at the beginning of September with the Bohr model of the atom and saw that it was inadequate. Sommerfeld put in a few patches, came quantum numbers, Aufbau principle, multi-electron atoms. Then we could explain the patterns in the periodic table, and then we posited octet stability as something that atoms strive for. And that gave rise to, first of all, just inert gases, explained them, but then we said, you know, things might engage in electron transfer. We could describe ionic compounds, then electron sharing, covalent compounds. Then we talked about metals, which is 75% of the periodic table, and en route saw the van der Waals bonds as a fourth type of primary bonding. And then we looked at secondary bonding, which is prevalent in covalent compounds, and we saw these three types: dipole-dipole, London dispersion, and hydrogen bonding. And ultimately that allowed us to decide whether something's a solid or liquid or a gas at a particular temperature. And we're particularly interested in 3091 since this is solid-state chemistry, the circumstances under which something is a solid. So up until now, I think you're comfortable with classifying materials on the basis of their bonding type. In other words, it's a covalent solid or an ionic solid or a metal. But I want to show you a little more interesting way of classifying, because we're going to classify things according to atomic arrangement. And so if you'll flip over the sheet, we'll talk about atomic arrangement and how it plays into classification of solids. By the way, solid, let's define solid. Solid is something that is dimensionally stable. It doesn't flow under its own weight. Has a volume of its own, whereas a fluid, either a liquid or a gas, takes the volume of its container. The fluid goes to the walls of the container. The liquid, in a gravity field, sinks to the lowest point in the container, but the container determines the shape. A solid retains its shape. So now I want to classify solids by atomic arrangement. So I don't care if they're metals or ionic compounds or covalent compounds. There's two classes, ordered and disordered. So isn't it nice when you can take things and classify them, just bifurcate? It's one or the other, and just move through that decision tree. So let's look at ordered solids. Ordered solids have a regular atomic arrangement, whereas disordered solids have a random arrangement. I put an asterisk next to random because it's not totally random. There's some local order, but there's no long-range order. So the order is short range. And what do we call such solids? The ordered solids are called crystalline solids. And we have a plain word, everyday word for such an ordered solid. It's called a crystal. And I've been using that term a lot. I talked about Davison and Germer irradiating a nickel crystal. Well, that's to distinguish the material from something that's disordered. If it's disordered, we say that the atomic arrangement is amorphous. And there's a simple Anglo-Saxon word for an amorphous solid, glass. A glass is an amorphous solid. You might think glass has to do with whether something is transparent or not, and I want to disabuse you of that. We've talked about transparency. And what do we know about transparency? If we want to talk about transparency, if something is transparent, what do? We ask ourselves, is the band gap in that material greater than 3 electron volts? If the answer is yes, it's transparent. If it's less than 3 electron volts, it's an absorber. So then what does glass mean? Glass means no long-range order. No long-range order. Let me give you some examples. We could say, for example, we've got diamond. Diamond is crystalline. Diamond is crystalline. And yet it's transparent. It's transparent. Why is it transparent? Band gap is about 5.4 electron volts. Obsidian. This is a glassy rock. It's got no long-range order. It's an amorphous material, and it is opaque. Obsidian is opaque. So here's an example of an opaque glass and a transparent crystal. So as of now, I want to make sure that nobody in 3091 from this day forward ever says glass is transparent. I will show you before the end of the month metallic glass. Metallic glass. How can it be a metal and glassy? Well, it must mean that there's metallic bonding operative, but the atoms are not in a regular arrangement. And that material is not transparent to visible light because you know that metals have no band gap whatsoever. So something important here. Something important here to retain. So the parents will now learn what the students have learned. When we go into a new unit, we begin with a history lesson. So let's go back. In the Wayback Machine, we'll go back to early efforts at trying to describe ordered solids. So that's why crystallography is the study of ordered solids. Crystal comes from the Greek. Crystallos, which is one of the terms that might refer to ice. It's a certain form of ice, but anyways, that's the origin. So let's go back to the first marking point in history. Robert Hooke. Robert Hooke, back in 1660, was studying cannonballs. They were doing military research already back then. What do you think? And he posited that a crystal must owe its regular shape to the packing of spherical particles. Packing of spherical particles. So if you pack regularly, you'll get long-range order. And then about a decade later, there was Niels Steensen, who was a Dane, spent most of his scientific career in Italy, and he observed that quartz crystals had the same angles between corresponding faces regardless of their size. And see, what they were looking for is trying to make a connection between the macroscopic and the atomic world. In other words, here's a simple question. If I see something has a macroscopic shape, very regular and cubic, can I infer from that that if I divide, if I get down to atomic dimensions, there will be some cubic repeat unit? Yes or no? That's the question they were wrestling with. And then around the end of the century, Christian Huygens, in 1690, studying calcite crystals, made drawings of atomic packing and bulk shape. And here's a drawing from his book in 1690. And Tom, if I could have if you could switch the video over to the document projector. I've got a calcite crystal here. Here's the calcite crystal. All right, and now autofocus. Autofocus is off. Autofocus is on. Okay, so now you can see this. Look at the regularity of this. Imagine you're looking at this. This is all you have to work with. There's no scanning electron microscope. There's no nanoscope, nothing. That's what you've got to work with. And what he comes up with, Tom, if we could go back to the computer video, please. So starting with that crystal, this is what he posits. That's not bad. Remember, this Huygens is the same one that gave us optics. You see, these people were polymaths. They weren't narrow specialists. They were generalists. And they made substantial contributions in more than one field. Tom, let's go back to the document camera. Let's go back to the document camera. Here's a piece of tin. All right? So, I mean, if I had to draw this piece of tin, I might draw a different drawing from what Huygens drew because you can see the angles are different here. Look at these are right angles. Well, here's a piece of beryl. This is beryllium aluminum silicate. Look at that. That's a hexagon on end, almost. Huh? So what's going on? Here's a piece of cryolite. Looks like somebody borrowed it and dropped it. Look at that. See? Bad data. Imagine drawing that. See? That's what happens. They give you lousy samples, expect you to do cutting-edge research. What do you do? Okay, Tom, let's go back to the computer before I digress. All right, so here we are. Here's another example. I couldn't bring this one in. These are big chunks of basalt off the coast of Iceland, and you can see they have other forms. All right. So far so good. Now let's go into about 100 years later over to France. This is René Just Aoui, and he's studying at Sorbonne, and he's studying the cleavage of calcite. Basically what he does is he comes into work every day and he breaks things. Okay? And he breaks the calcite, and he looks at the little pieces of calcite, and what he observes is that all shards are rhombohedral. It doesn't matter how small he breaks the calcite crystal down, he always gets rhombohedral shards. So then he says, I'm going to posit that that's the base unit of calcite. And furthermore, because he's a Frenchman and they're steeped in mathematical tradition, he decides to model this mathematically. And he says, okay, we all know that if we wanted to fill 3 space with the same unit, we could choose a number of shapes, right? We could start with a cube, and I could fill this room with cubes of identical size. I could fill this room with sort of orthorhombic boxes, sort of rectangular but square cross-section. I could have something that's rectangular with a rectangular cross-section. I could use something that's rhombohedral. How do I know? Look at the crystal. I don't see any holes here. Okay? So what Aoui did is he said, mathematically, I want to determine what is the maximum number of distinguishable shapes that will fill 3 space. I call this the milk carton problem. How many different shapes of milk cartons could you make that would you be able to fill the truck perfectly? And he came up with 7 of them. 7 of them. And I'm getting ahead of myself there. The 7 of them are shown here. This is in your notes, and these are the labels for them. And here's the basic unit. So you have 3 lengths, A, B, C, and you have 3 angles, alpha, beta, and gamma. And depending on which mix you choose, for example, the cube is here, A equals B equals C, so 3 edges, all normal to one another. And then here's orthorhombic, they're not equal to each other, and so on. So 7 basic shapes. And here they are drawn for you, and this is taken out of the lecture notes, the archival lecture notes. So this is analogous to the tiling problem, just to drive home the point. So if you want to do the tiling problem, how many distinct shapes of tile are there in 2 space? All right? So I think we can agree we can go with square tiles, all right? Or we could go with rectangular tiles. What other tiles do we have? Triangle. Well, triangle is actually, it's not a basic unit because it doesn't observe translational symmetry, but if I close the triangle like this and have a 60 degree, so this will become the basic repeat unit, okay? Then there's a regular parallelepiped where this unit, angle rather, is not equal to 60 degrees. And this, in fact, is the basic unit that Frank Gehry uses in building his. If you go over to the Stata Center, you will see that the basic unit that's used to make those irregular shapes is this. Well, this is space filling, and all of these are labeled and so on. This is the clothing problem. How do you cut a 2-dimensional piece of cloth to fit over a 3-dimensional shape? It's not a trivial problem. That's why most clothes don't fit. Because it's very simple. Fashion designers don't understand the simple geometry. Right? You know, and we have, how do we describe size? You know, for men at least, they take a chest size and a sleeve size. For women, they just go, oh, she's an 8. Well, an 8? One number? You know, this is why things don't fit. You know, you have to get down to the unit cell. Here's one that won't work. The pentagon won't work. And I'm not trying to make a political statement. I'm simply saying that. So here's what you can do is here's what happens if you try to fill 2 space with a pentagon. You see it won't butt up. There's these white gaps. The reds touch the reds, but it won't fill. So this is how OE worked in 3 space and determined that certain units will not butt up against one another and fill 3 space perfectly. Okay, so we're clicking. Things are going well. But we still haven't got atomic arrangements. All we've got is milk cartons so far. So now let's think about the next step. The next step came about 50 years later, in 1848, which was an auspicious year in Europe. It was another Frenchman, Auguste Brevet, and he proved mathematically that there are 14 distinct ways to arrange points in space. And what do I mean by that? Here's a cartoon that shows the cube. We've agreed that the cube is a cookie cutter that will fill 3 space. But when I start putting atoms in the cube, I have 3 distinguishable arrangements. So here on the left, I have something where I put atoms only on the corners. And the second one, I put atoms on the corners and one in the center. Now look at the one in the center. That one in the center sees 8 nearest neighbors. Each one of these see only 6 nearest neighbors. So these atoms have a different atom arrangement, a different atom environment from the atoms in this arrangement. So the left one is called simple cubic. The center one is called body-centered cubic because there's an atom in the center. And it doesn't matter. I can arbitrarily shift the center up to this corner, and this corner atom sees the same nearest neighbors in the same arrangement relative to the center. Here's body-centered cubic. Choose any one of those. If I sit here in the center, I've got 1, 2, 3, 4, 5, 6, 7, 8. Or I can go to this one over here, and it sees 1, 2, 3, 4. And then you just keep going, it's going to see the same arrangement. And yet the cookie cutter that fills space is the cube. And yet there's one other possibility, and that's face-centered cubic. Face-centered cubic is here, where you have the square face and then an atom in the center of each face. And that's distinguishable. That's distinguishable. So Brevet, again, Frenchman, steeped in math, goes into the mathematics and asks, how many different ways can I put atoms into these 7 crystal systems that Aoi has specified and get distinguishable point environments? And the answer is 14. The answer is 14. 14 ways to arrange points in space. So now we're getting somewhere. Now we're getting somewhere. And by the way, if you look at this, here are the 14 different Brevet lattices. And they're showing, this is also from the lecture notes. And all we're putting here is 1 dot at each lattice point. But it doesn't have to be a dot. Okay? What I'm going to show you in a second is I can put sets of atoms, groups of atoms. In other words, if I wanted to describe the positions of every apple in an orchard, what I could do is say that the Bravais lattice is telling me the planting of the trees, and then I can hang different types of apple arrangements at each point. So this is what we're getting to. We're trying to break this down. Otherwise, we're going to have a gazillion different atomic arrangements. And what we're able to do is confine everything to a simple set of 14. So what I want to do now is show that we can look at different sets of elements at these points. So let's see what happens if we look at face-centered cubic and put different atomic groupings at each point. So ultimately what I'm in search of is the crystal structure. The crystal structure. And the crystal structure is the atomic arrangement in 3 space. Atomic arrangement. And the crystal structure is the sum of 2 components. First is the Bravais lattice. The Bravais lattice. And what the Bravais lattice is, it's really just a point environment. It's a point environment. And I can put anything I want at the point, including nothing. I mean, I can make this the equivalent of a John Cage piano piece, you know, with just a bunch of rests of different time signature. You know what I'm talking about? Listen. That's rests in 4/4 time. See that? Okay. See this? That's a simple cubic lattice. It's a set of points in space. Okay? So it's a point environment, but let's hang something on the points. And what we hang on the points is called the basis. The basis. And this is the atom grouping. The atom grouping at each lattice point. This will all become clear, I assure you, with a few examples. So let's look at some examples. Well, let's look at examples, say, for face-centered cubic. Now, let's see what we can do with face-centered cubic. So I'm going to choose, in all cases, the Bravais lattice. The Bravais lattice is FCC. So that's showing up there on the right side. Only what you're seeing here is the drawing with just a single atom at each lattice point. Single atom at each lattice point. So if the basis is something, just a single atom, so that could be a metal. So an example for that might be gold. See, this is gold. This is a Bravais, FCC Bravais lattice with 1 atom at each lattice point. How do I know it's gold? Look at the color. It's obviously it's gold. That's how I know. That's FCC gold, but there's a whole bunch of metals that are face-centered cubic, including aluminum, copper, platinum. These are all FCC metals. Okay? And so in this case, we would call the crystal structure is also FCC because you've only got 1 atom per lattice point, so the lattice point and the Bravais lattice and the crystal structure are the same, face-centered cubic. I could put a molecule. I could put a molecule at each lattice point. For example, methane. I could put the 5 atoms, carbon and the 4 hydrogens, at each lattice point. And if one of you is the first human to go to Jupiter, when you get to Jupiter and you see solid methane, you'll be heartened to know that it will be in the FCC crystal structure. It has to be. Even proteins, even DNA, if it partially crystallizes, is going to crystallize in one of those 14 Bravais lattices. It has to. Huh? So solid methane, and this will also be FCC. We can put an ion pair. An ion pair, for example, a cation and an anion at each lattice point. And that would give us sodium chloride, and sodium chloride gives us something that's called the rock salt crystal structure. And this model here is sodium chloride, where the greens are chlorine, and the golds here are sodium. And what you do is you might say, well, look, they describe a square, so why don't we just call this simple cubic? But if we call it simple cubic, I have different atoms at different lattice points, so that won't work. Instead, if you can just train your eye to look at the greens, look at 1, 2, 3, 4, 5. There's a 5th green in the center of a square. Then train your eye to look at the golds. 1, 2, 3, 4, make a square, 5 in the center. So instead say, let's look at the pairs. Green and gold, 1. Green and gold, 2. Green and gold 3, green and gold 4, and green and gold 5 in the center make a simple cubic, a face-centered cubic lattice with a rock salt crystal structure. That's shown here in this cartoon. So whether you count the greens or you count the blues, it doesn't matter, but it's the ion pair. So that means this is a derivative from the FCC Bravais lattice. And then there's one other one. There's one other one. I can put an atom pair. I can put an atom pair. Here I put 5 atoms, a molecule. Here I'm going to put an atom pair, and the example I'm going to give you is 2 carbons at 109 degrees. And what will that give me? That's an example of diamond or silicon or germanium. And here's diamond right here. This is diamond. If you train your eye, the atom that I'm holding has 4 struts coming out of it. That's the sp3 hybridized, 4 struts coming out of a single carbon. Every carbon has 4 struts coming out of it. But watch this. When I lie this down in a single plane and I bring it up, you see where I've got the post-its? Look at how the post-its describe 1, 2, 3, 4, 5. It's face-centered cubic, and with each lattice point I take 2 carbons. 2 carbons here, 2 carbons here, 2 carbons here, and I go all the way through the lattice, and I end up with diamond cubic crystal structure as a Bravais lattice with a basis of the atom pair, and this is diamond cubic. So diamond cubic is the crystal structure, but it's derived from an FCC lattice. So again, the overarching theme here is the integral of the Bravais lattice. This is the set of points, right? This is the point set in 3 space, the Bravais lattice, and then what you put at each point gives you the crystal structure. And you can go on and on and on. You can have a ball with this stuff. Oh, here, this is to show you in 2 space. This is an interesting one. This is an Escher print. This is a dog's. So what's the crystal structure here? So let's start looking. Well, you might go 1, 2, 3, 4, 5. You might say, well, this looks like simple face-centered cubic. Actually, face-centered and body-centered are the same in 2 space, right? The body, this is, you know. So how do you describe a sponge in 2 space? Think about it. Okay, the trouble is this dog's facing in the other direction, so that won't work. So instead, all these dogs are facing the same way. And now if you look carefully, take as the basis, see those could be lattice points. The Bravais lattice is the red dots. The basis is the set of 4 dogs. The 2 facing the right and these 2 facing the left. Now 2 right, 2 left, 2 right, 2 left. So it's the 4 dog set. You know, those 4 dogs are the basis, so bingo. So now what do we have? We have simple cubic. This is SCP, simple cubic puppy. That's a 2 space, all right? Look at this one. I put the dot here on the abdomen of this creature. Okay? So, what do you got? This is a rhombus. Okay? Or some of you might initially have called this the triangle, but you see that when you put the 2 of them together, this has translational symmetry. And in fact, look at how many of these entities belong to that lattice point. All of this, all of this, all of this, because the tail to this is up here. So the repeat doesn't start until down here. You could cut it this way, I don't care. But the point is, this is the concept of the basis. The basis is many, many units that are repeatable and can be positioned at each lattice point. So now what I want to do is talk a little bit more about the cubic system, because we're going to focus on the cubic system in 3091, largely because it has a simple geometry. Most of the periodic table you'll find is in cubic system, FCC or BCC, and then the math is simple because you're in Cartesian coordinates. So let's take a look at what we've got going for us here. I want to look at the properties of cubic crystals. So here we are. This is a table out of your lecture notes, and I'm going to work through this table, and I urge you to get friendly and comfortable with this table so that you understand the properties. And why? Why am I making you learn this stuff? Because I think it stands to reason that if you look in this crystal, you see that atoms touch along certain directions, and atoms are far apart along other directions. Well, we've already seen in 3091 that there's a correlation between atomic contact and bonding. And bonding is related to a whole host of other properties. For example, mechanical strength. There are people in this room that are thinking about being mechanical engineers, aeroastro engineers, nuclear engineers. You need to understand the relationship between the crystal structure and the strength of the material. Obviously, if I look down an atom direction, where I have a high density of atoms, that's going to be a direction of strength. If I look down a direction that has a low population of atoms, that's going to be a direction of weakness. And then subsequently, if I want to cleave a crystal, then where am I going to cleave it? I have to understand the crystallography, the electrical properties, the optical properties. What's the index of refraction? It's the bending of light in response to the field set up by the bonds. So if you want to go into optoelectronics, you better know this stuff. Everybody has to know this stuff because chemistry is central to everything. It's all chemistry. This conversation is brought to you by secondary bonding. That's all. That's it. So let's look at this one in some detail. And what I want to do first of all is the unit cell. Let's look at the unit cell. So here's FCC, face-centered cubic. So there's the lattice. And now what I'm going to use is a hard sphere model. So I'm going to make the spheres, the atoms, so big that they actually touch along their principal axis of contact. So face-centered cubic, the atoms touch along that face diagonal. And the unit cell, this is called the unit cell. This is the repeat unit. This is the unit cell is that which repeats in 3 space and fills 3 space. It's the basic unit of the crystal system. And the edge of the unit cell is given the dimension A. So the edge of the unit cell, and this is a cube, so it's all the same edge. So the volume of the unit cell is equal to A cubed. That's trivial. So we got that. Oh, lattice points per unit cell. Lattice points per unit cell. Let's look at that. Let's look at this, this red one. How many lattice points? Well, we can count lattice points by counting atoms. If you see, there's 8 corner atoms. And how much of each of those corner atoms lies within the bounds of this unit cell? It's 1/8. Okay, so lattice points per unit cell is going to equal 8 times 1/8. This is the corners. This is the corners. And then we've got these face atoms. 8 times 1/8 is 1. And you see these blue ones? These blue ones are half inside this unit cell and half inside the adjacent unit cell. And I got 1, 2, 3, 4, 5, 6 of them. 2 in this direction, 3 principal directions, and 2 times. So that's 6 times 1/2, which is, this is the face atoms. Okay? 6 times 1/2 is 3, so 3 plus 1 is 4. So I have effectively 4 lattice points per unit cell. I'm not saying atoms because I could replace each of these single atoms with a methane molecule, so then I'd have 5 atoms per point. So that's why I'm being a little bit fastidious here. Lattice points per unit cell. What else are we looking at? Oh, nearest neighbor distance. Well, nearest neighbor distance, that's kind of obvious. Here's a drawing. This is A, and that distance is root 2 times A, and this is half of root 2, so that's given here, A over root 2. Nearest neighbors, well, you can see that. Nearest neighbors, let's count from this one. It's got 4 at the corners, right? And it's got 3 in this plane and 3 in the other plane, so that's going to add up. 4 plus 4 plus 4 is nearest neighbors is equal to 12. Some people call this the coordination number. Coordination number. And this has got the highest number of nearest neighbors when you have hard spheres of equal dimension of any crystal system. You can see here in body-centered cubic it has 8 nearest neighbors, whereas simple cubic only has 6 nearest neighbors. Oops, I don't want to look at that anymore. All right, and then the packing density. I want to show you the packing density. That's an interesting calculation. What the packing density indicates is how much, going back to Democritus, if we model the FCC crystal as hard spheres touching, how much of this is matter and how much of it is free space? Well, that's given by the packing density. Packing density. And that's equal to the volume of the atoms divided by total volume. Total volume. So if we choose the unit cell as the basis, so we've got something to count on, let's go back. So we know that let's go to the other one. I like this one. It's a cuter drawing. Okay? So the volume of the atoms, well, I know I've got 4 atoms, equivalent of 4 atoms. And what's the volume of an atom? It's going to be 4/3 times pi times the radius of the atom cubed. And what's the volume of that unit cell? That unit cell is A cubed. And now I need to know the relationship between A and R, so I can convert one to the other, and then I'll have a dimensionless group here. So there you can see the relationship between A and R. A squared plus A squared is the 16R squared. So if you go through all that, you can convince yourself that A equals 2 roots of 2R in FCC. So plug that into there, and you'll end up with the packing density will be equal to pi divided by 3 times the square root of 2, which is a value of 0.74. So that means in face-centered cubic, in a face-centered cubic lattice, you have 74% matter. This is assuming hard sphere model. Hard sphere model. Spheres so big that they touch. So that's 26% void. 26% void. And you can go through and you can see that as you look at this table that the packing decreases. In the case of body-centered cubic, there's a little more open space. It's 68%. And in the case of simple cubic, it's only about half packed. So this table here is something that you want to get good and friendly with. Other thing I need to show you is crystallographic notation. And what I think I'm going to do is invite you to look at the website. This will give you the nature of the crystallographic notation. Position is basically as it is in your math classes. The only difference is we don't put enclosures. There's no parenthesis around a point. So if the origin is 0, 0, 0, but don't put parenthesis around it. So a point is simply written as follows. So origin for a point, 0, 0, 0. That's all there is to it. In the case of directions, this is going to take a little more time than I have set aside because I've got a few items of business that I need to take care of. So I think I'm going to hold at this point, and we'll jump ahead to this is. See, I always have a few things up my sleeve. Okay, so let's go back to the beginning. When people came in, as is the custom, we have music playing, and what was the music today? Yeah, the Talking Heads, and the song was Burning Down the House. So why would I be playing Burning Down the House in a lecture about crystallography? Well, what inspired me to choose that piece of music was this painting, The Houses at L'Estaque. This was painted by Georges Braque in 1908. L'Estaque is a community down in the southern part of France. And when Braque painted this, he outraged the critics of the Salon in Paris, who condemned this painting. They said, look, it doesn't have a common perspective. The houses in the back, it looks as though the lighting is coming from here, but then the lighting over here is coming from another angle. He broke all sorts of artistic conventions. And one critic ultimately condemned this painting of houses as nothing but a stack of cubes. And from this came the term cubism. And since we've been talking about the properties of cubic crystals, I thought the connection was pretty obvious. Okay, I did. All right. We have a contest every year in 3091. The contest involves developing a mnemonic device for the certain groups in the periodic table, the lesser known actinides and lanthanides. And so I'm going to announce the winners today, and we'll see if they come to class. But in their defense, there's a second lecture. So if they're not here, we assume that they're at the second lecture, right? So anyway, so here's one. This was for the lanthanides. This was an Elizabethan sonnet that was written by Alison Burke. Is Alison here? She obviously goes to the second lecture. Okay, so just so you'll see in a minute what the prizes are. Okay, next one, Eddie Fagan. Is Eddie here? You have to come down and claim your prize. Come on down. Okay, so he has a choice of two items. One is the, congratulations. Okay, but I haven't shown you everything. First, here's his mnemonic verse, but this is really hot. Look, one of the things that we learn is the Born exponent, and but what's really cute is, I mean, I didn't notice this the first time, I just caught it last night. So this, of course, is a pun on the Born identity, but down here, it's 3091 Pictures is in the corner here. Very sweet, very sweet. Okay, so you have a choice of, the hot necktie from the American Chemical Society, or this is a beautiful, this is a lady's scarf. Don't know. You don't know what's going on in his personal life. What are you talking about? Come on. But you know what I'm going to do? You're not going to make the choice right here in front of all of these people. You're going to talk to me afterwards, and they're not going to know what you chose. Perfect. Okay. Okay, so the one that I'm choosing as the winner, I've had all sorts of things given to me over the years. The Elizabethan sonnet is one, but this is the one that takes the cake. This one, this is a musical departure, a riff on the Nat King Cole song "Love," and this is an image of the CD. She turned in the CD to me at minutes before 5 o'clock on the deadline date. Okay, so I have this. This is the image, and there's the words. Listen to this phrase here. It imitates very, very in the song. It's beautiful. Yeah. So it's really good. All right, is Ms. Gabriel here? Please come down. She obviously is also, she's either here or she's shy or she goes to the 1 o'clock class. Anyways, I wanted you to see, and I want you to understand that this is part and parcel of what makes this student body unique. I mean, I submit that this kind of thing would not happen at Harvard. Okay, a couple more things. Tom, could I get back to the document camera? I want to show some other crystals and make the point about symmetry and so on. So this crystal I'm going to show you is cryolite, and cryolite is birefringent. I'm sorry, I'm going to have to ask you to go back to the thing. I needed to show this one thing, please. Tom, can we go back to the computer? Thanks. Okay, so what I'm going to show you is something that's birefringent. The crystal symmetry has atoms just in parallel, a little bit off axis from one another. And what that does is it gives rise to two indices of refraction. And so if you have a light ray entering the crystal off the alignment of the optical axis, the light will split into two. So you'll get an ordinary ray and an extraordinary ray. And the separation of these two rays is related to the difference in the indices of refraction. Now, if you're in optoelectronics and you're making a splice and you've got a material that's birefringent, you better know this. Because all of a sudden you got your light going off to the side, or maybe this is what you want. See? So what I'm going to show you is, now we can go to this. This is a piece of cryolite, and it's birefringent. And what I'm going to do is show you how it will act on, if we can go to this, where am I? Okay, I'm here. Good. Let's see, can I zoom in any more? Good. And now what we'll see is, as I turn this, you see now I've lined up. So do you see this line here appears as a line? Everything's as it should be. But then as I turn this, cool, see that? Separation. And then I can bring it back. So that's birefringence. And this is another example of what you get with crystal that is has a particular crystal structure, one of the rhombohedral types. Back to the computer, Tom. I got to set up one other thing here. Okay, so this gives you an indication of some of the materials that you may know that are obviously calcite. Ice is birefringent, not terribly so. Rutile, very much. Titanium dioxide, one of the forms of titanium dioxide. Quartz, just mildly so. Okay, now I want to show some very strange FCC. This is colored golds. You know what gold looks like. It's very malleable. It's an FCC crystal, and yellow. By alloying with different elements, you can change color. Right? But these are all FCC. You see, nickel's FCC, aluminum is FCC, and indium, so on. What I'm going to show you is the alloying of indium with yellow gold to give something that is 12 karat gold. So, Tom, may we switch to the document camera? Okay, let's get the cryolite out of the way. This is gold. This is the gold foil that Rutherford would have used in his famous experiment. Okay, and now this is indium gold. It's a very soft, sort of a dove's egg blue color. Very lovely color. So you might ask yourself, well, what could you do with something like this? Because it's somewhat brittle. You can see here's the machining. That gives you a better sense of it. Just a little bit off. All right, so what I was thinking is, what if we were to do something like this? We could take a watch like so, see this? And then what we could do is put something like that here, see? And then we put quartz movement underneath, and we put some numbers on the front here and some hands. This thing's solid 12 karat gold. We could sell this thing for about $10,000 a piece. And then there's all those other colored golds. We could do all of this as well. So I think this gives you a sense of what happens when you understand crystallography. And I think with that, we're going to go for an early dismissal and wish you a good weekend.